Hi. Okay, one more example here for you for solving moments. This is going to be another example using 3D moments, and I'm going to solve this one in the opposite direction. I'm going to do the scalar approach first, and then use the vector approach. So I've mentioned this a few times, but I'll never require in the assessment that you use scalar over vector. I'm just trying to get you to see the different ways to sort of view and approach these problems. And so understanding both of them is going to be helpful for yourself, but also for when you're talking to your classmates and trying to understand the way that they're approaching a problem. So let's start this time with the scalar method approach and then reiterate it with that vector approach. I've said this possibly in a video, and I know I've mentioned to a few people, but I like the scalar method. Once I figured it out and it clicked for me, I liked it because I think it's more tangible. It's easier to be able to understand and explain physically what's happening when you think about it in the scalar approach than the cross products. Because at least for me, maybe one of you is better at this, the cross product is so mathy. And the reason that I like engineering is how practical it is, right? So I want to be able to talk about rotating. I'm going to turn around. I have some cabinets here, but right, this is rotating around an axis here. And to me, that's more tangible than saying that a moment has an I, J, and K component. Sometimes calculating it using the I, J, and K component clicks with the way that our brains like to do that sort of math. But I think once you can explain it using a scalar approach and understand what that I, J, and K component mean for the moment, it becomes a little bit more powerful. I hope that helps. But let's solve this problem. And we're going to keep practicing this all quarter. The moments and 3 dimensions are not going anywhere. So let's just get comfortable dealing with them. Okay, so now I will admit that some of these examples are a little bit like, when would I ever come around this situation? But again, they get to the math and might help you understand it a little better. So we have a 12-foot boom that is fixed at end A here, which is the origin. And it has a steel cable stretched from the free end B here. So this is B, and it has, just going to give the coordinates here. This is 1200. And it's stretched to C, which is located at 0, 4.8, and -8 in the Z. And we want to determine the moment about A of the force exerted by this cable at B. So we have a force here. We know the magnitude of this force, which is 384 pounds. We want to determine the moment of that force exerted at point A. And that's important. We're going to start seeing this next week. That's important because this here is a connection. This is going to be a weak point in our design. And so we want to know what that connection is feeling so we can pick a rod, or really a connection from the rod to the wall that can support that, so that this doesn't break, so that it remains in static equilibrium. That's our goal in this class. Okay. But in order to do that picking of the external support, we need to know how to calculate these moments. So that's what this module is about. Okay, so let's do this first using a scalar approach. Before we even get there, I'm going to need to know some of these vectors. So I'm going to write out some vectors. The first vector that I am going to write out is the position vector from where? Well, I'll just write it. We're going to need it later when we do the vector approach, is from A to B, right? From A to B. We could do A to C, but A to B. And that's going to be 12I plus 0J plus 0K. We'll keep that in our back pocket. But I also need to write the force from B to C in 3 dimensions. And you need to, in IJ and K components, and you need to do this for both the scalar approach and the vector approach. So when you do the scalar approach, you still need the components of the force. That's what we're doing here. Okay, so I know the magnitude, it's 384. I'm going to multiply that by the unit vector, which is the position vector from B to C divided by the magnitude. So to get from B to C, I need to go -12 in the x direction, and then a positive 4.8 in the y direction, and then a -8 in the z direction. And I'm going to divide this by the magnitude, which I will just cut to the chase and you can calculate for yourself, is 15.2. Again, remind yourself what that 15.2 is. That 15.2 is the distance from B to C. It's the distance of the cable. It's the distance from B to C along the cable. Okay, and I'm going to write this out in its component form. This is -303.2 I hat plus 121.3 j hat minus 202.1 k hat. So that's the force. Okay, let's go back over and calculate the moment about point A using a scalar approach. And so I'm going to do that by looking separately about how this force is causing moment about the x-axis, the y-axis, and the z-axis that goes through that point A. Okay, so I'm going to start with my x-axis. And I did this example in a previous video. You can go back and look at the lesson 10 videos. So x-axis, let's smash that x-axis. We're going to take this whole thing, and this one might be easy to visualize because I'm smushing against the rod. So I'm taking the rod and smashing it right up to the wall. And what I'm left with is a set of axes that looks like this, y and z. X would be coming out towards you. And if I do that, where would my force end up? My force is going to look like this. It's going to go right through the origin. So can that force in the force from the y direction or the force in the z direction cause a moment about point A? My point A is still right here. The answer here is no. There's no moment about the x-axis because there's no force acting any distance away. Remember, in order to have a moment, we need a distance, a perpendicular distance away from that point. It can't cause a moment if the force only goes through that point, if the line of action of the force goes through there. So there is no rotation along that rod. It's not going to spin. If this is that rod, the rod is not going to spin. That rod happens to be on the x-axis. Okay, great. 1 down, 2 to go. Let's look at the y-axis. So now I'm going to smush this from the top down. So now you're kind of looking at it from above. If you do that, your set of axes is going to look something like this. And so if you do that, your force is going to end up, it has a negative x direction, so it's going to point up, and it has a negative z, so it's going to point to the right. So my force is going to look like this. Its components are in the x direction 303.2 with a negative, and then the y 202.1. And that distance that I need to represent is 12. So I'm going to now determine the sum of the moment about this point A. And I'm going to assume that anything in the counterclockwise direction is positive. And so only the z component of the force is going to cause any rotation, because the x component, again, goes right through point A. So this is going to be, did I mess that up? I did. I messed that right up. No one was here to tell me otherwise. So let me erase these because I mixed them up because I'm not used to my x going down. Okay, so this one needs to be 202.1, and this is the 303. Maybe tell. All right, so the moments about point A is going to be 202.1 times 12. Now, this is where I need to think about direction and not automatically put in the negative sign that was there on the force. This is going to cause rotation. If you think about a piece of paper, if you held a piece of paper, I'll hold this. Okay, if you hold a piece of paper, this is A. Now this is going to be mirrored. So think you got to trick your brain here. Point A is actually up here. And then I am pushing it. So I'm gonna mirror this so it looks right for you. Is that right for you? No, point A is there, yes. Which is point A? If I have a whole paper, I want it to be in my upper right, but that's looking backwards for you. But then that also, I don't know. This Zoom thing is really screwing me up. It's mirrored for you. Okay, so I'm gonna push here. And for me, that this is going, so maybe I shouldn't show it on the screen. Just do it too for yourself. You hold a something rectangular in the upper right. If you push on the left side of it and you push to the right, that is going to cause rotation in the counterclockwise direction, which is our positive. So this is going to remain with a positive sign. And this is going to be 12 times 202.1 is 2425. This is the y-axis, so I'm going to put a j hat here. And my units here are pound feet. Okay. And then now let's look at the z-axis. So again, we're going to smush the z-axis. So I'm going to end up with the y and x. My force in this case is going to go negative in the x direction and positive in the y direction. So it's going to look something like this. I'm going to need to know this y component, which is 121.3. My distance here is the same 12. And this is still my point A. I am going to determine the sum of the moments about point A. And this is going to be 121.3 times 12. Again, I'm thinking, okay, I have a rectangle. Now I'm holding it in the lower left corner. And I have a force and I'm pushing up on that force. And if I do that, I am going to cause rotation in the counterclockwise direction. So this should have a positive on it. And this ends up being 1455. This has a K hat on it and it's pound feet. Okay. So at point A, there is no rotation about an x-axis going through point A, but there is some rotation about the y-axis. So thinking in 3 dimensions and the way that this coordinate system is, that's going to be sort of twisting the whole thing, like the floor twists around something like this. Like your y-axis is up, this door twisting around, that would be around the y-axis. But at the same time, there's rotation as if you were lifting up a trap door. So both of those are happening at the same time. And that's what the scalar method is showing us. Okay, let's solve it now using the vector method. So the vector method, we are going to find the moment about A by doing R of AC, although you could also do R, sorry, not RAC. You could do RAC. We are going to do RAB because it's easier, and we're going to cross that with FBC. I'm going to write my determinant. Always needs to go in the right order. So I have IJK on top. Then I'm going to have my R, which is 1200, and then my force, and I am going to put in my signs here. So it's negative 303.2, and then 121.3, and then negative 202.1. If I do this determinant, I'm going to have I hat, and that is going to be multiplied by 0. So it's 0 times something minus 0 times something, which is 0. Then I subtract J hat. And when I look at the J hat, move this black. When I do the J hat, I need to multiply 12 and negative 202.1. So I have J hat times 12 times negative 202.1. Then I would subtract from that 0 times negative 303.2. So I'm going to ignore that. Then I add K hat times 12 times 121.3. You do this, you end up with 2425 J hat plus 1455 K hat, which by no accident matches what we found using the scalar method. 0, 2425 around the y-axis and 1455 around the z-axis. Okay, hope this helps. Hope this reiterates the difference between scalar and vector method and sets you up for success to do really well on the Module 2 quiz. If you have any questions, please reach out, email, discussion board. I will be checking those as often as I can tomorrow, depending on all the things, all of the drainage of the sinuses and all that. So I hope you all are staying well and doing okay in all your other classes. And I will see you as soon as I possibly can. Okay.